students, welcome back. Now, I think only one lecture is remaining for today evening. That is called field effect transistor biasing techniques. Let us understand how to bias the transistors using field effect transistor methods. BJT class is somewhat tough for us because it has a non-linearities, temperature effects, so many things are there. But these devices are very comfortable. They are temperature-wise, they will not get disturbed. So that's why it will have a good impact of designing. Very easily you can understand the biasing techniques. Let's say three biasings are there. First we will go for depletion biasing technique. Then we'll go for enhancement biasing techniques. Okay. First let's start with depletion technique. You can see. Very good evening. Who is this? Kamlesh. Very good evening. Let's start biasing techniques. The first technique we are talking about depletion, MOSFET, otherwise JFET. For both these things, same biasing technique. So if you study depletion MOSFET, you know how to solve JFET biasing. So both will have the same impact because both are under depletion mode. So first topic we are doing is fixed biasing we are doing. So how to design operating current and voltage by fixed bias circuit. Let's see how the fixed bias can be designed. This is RT, this is VDD. We are having here a resistor RG with a negative battery. I'm applying what? VGG. This is gate, this is source. This is your ID current, this is your VGS voltage. So you can see the first design called fixed bias circuit. Yeah, this is called fixed bias circuit. Please note on it. Can you observe some important points in the diagram? I'll ask you please try to understand what is the new things I'm seeing in fixed bias circuit. In BJT class, fixed bias means only we have VCC supply. We have one RC resistance, one RB resistance like that. But in this class, I've seen that there are two different batteries he has taken in fixed bias. One battery is a positive battery, which is called VDD. One battery is a negative battery he has taken. What is the reason for that? Why should I take two batteries? What is the problem you have? Because input he is asking in depletion MOSFETs or JFET, input should be reverse bias is asking. If you want input reverse bias, we need a reverse battery separately for that. But if you ask forward bias, simply I'll take a resistor like this and I'll make that VGS positive. But there is no chance for me that from VDD I can make reverse bias. That's why the main target for depletion mode is you have to keep always VGG or VGS as negative in the class in depletion mode. So here VGG is there. So one thing now you can write from the board. Seeing this board, you can write that the current going to the MOSFET always will be equal to 0. This point is the first rule. Okay, why IC current is 0 means MOSFET is having a oxide layer in the between metal and semiconductor, so the current cannot enter, the current cannot leave. That's why MOSFET wise any current is going from the gate voltage, that current will take it as 0 in the classes because of the metal oxide semiconductor is having very high input impedance. Examiner has given suppose RG, VGG. Now you have taken the principle that MOSFET is having IC 0. Then what is the meaning of that is? Suppose if you take MOSFET like this. This is MOSFET. Okay, this is gate voltage. He's telling that the input impedance is very high in MOSFET is telling. How much the input impedance generally here is? Around 10 power 12 to 10 power 13 ohms nearly. This much of impedance your MOSFET is consisting. So you can say that this impedance is nearly infinite, you can say, because 1 mega ohm itself is a high impedance for us. You're telling 10 power 12 to 10 power 13 ohms because of the MOS. Because of your silicon dioxide layer, that much impedance I'm enjoying there. Because of this impedance, in general, we take always in the MOSFET, the gate voltage current will be 0. This is the principle we apply for enhancement MOSFET and depletion MOSFET in the classes. So straightforward I have taken with the principle IC is 0. Then how this model will be converted? This model we can rectify like this. We can modify as VGG. Next we have MOSFET. This is source. This is gate. And we have RT. This is VDD. RT VDD. This is the way you are seeing. In gate we have source and drain. So can you see that here one important principle is after applying IC 0, RG is becoming there. RG into IG, the drop is becoming 0 here. It's becoming a short circuit in the class. That means RG is getting disappeared in my next step because of gate current is 0. As the gate current is 0, okay. So gate current is 0. That means here the voltage drop, across RG. If I ask you how much across the RG resistance, it is IG into RG. Your IG is 0 into RG, it will be 0 volts. So that's why this resistance become a short circuit here. So the voltage drop across that RG will be 0 volts because no current is flowing to that resistance. So this model, just present the model like this in the exam point of view. Okay. Now what is the gate to source voltage? This is called operating voltage. This is called operating current. So if you want to find the operating points, if you want to find the operating point Q. So in this case, what is my operating point Q is? It is VGS Q, comma IDQ is my operating current and voltage because we are talking about transfer characteristics. So seeing the board, I can say your VGS Q is equal to minus of VGG. This is my first answer seeing the board. Okay, nothing to solve, simple problems. This voltage is same. So VGS is reverse bias by battery. Because in depletion MOSFET or JFET, we have to take input reverse bias. So I've taken a reverse battery for it. And I fixed that VGS I fixed it to this battery. That's why I got the name as fixed bias in this concept. Okay, in BJT class the style of thinking is different. Here the style of thinking is different because here reverse techniques we have to apply. So this is the story. So anybody ask you what is VGS Q, you tell in the exam it is minus VGG is the answer for it. First answer is completed. Next second point. Second point is what is IDQ? How to solve IDQ? Operating current, how to solve? I think it's not clear for you, this one. This one I'll write again. It is not clear. It is nothing but I've written VGSQ, comma, IDQ, operating current and voltages. In MOSFET, the operating voltage is VGSQ. The operating current will be IDQ in the class. Okay. VGSQ I found, IDQ if you want to find. you can go for the equation Kn into Vgs minus Vt whole square. We can solve. We just keep here Vgs cube. You can keep here Vgs cube. So if you substitute that Vgs cube, examiner will give Kn, Vts by themselves, MOSFET parameters they'll specify for you. Only thing is Vgs cube you have to apply. So where Kn is nothing but, where Kn I have been specified is half into nu n Cox W by L. I have considered in the class. Okay, I consider the Kn value like this. Somebody is telling logo is there, so I'm moving it. You can see. Now you can see it's clear, I think. Indra Kumar, I think this is clear now. Okay, so these are your operating current and voltage. But in MOSFET class, not only in this manner, we try to use graphical approach also sometimes, because mathematics is somewhat tough here. So graphical approach or graphical method to find out the operating point. So we'll see both the actions today. Circuit wise we'll calculate, and graphically also we'll understand. So this is called as a load line concept we'll apply. What is load line concept is? This is your graph you have to take first. VGS versus ID. You are having a graph. This is your threshold voltage. This is your experimental graph called as depletion MOSFET graph. Now the point is, the VGS Q, you just fix it to set a point here. On the x-axis, you fix the point as minus VGG as your VGS Q point. That means fixed bias is nothing but a point on the x-axis. For any point, there will be some straight line called load line. For any point, the load line is always vertical to y-axis. For x-axis point, the line will be vertical. For y-axis point, it will be horizontal. So this is called load line. Vertical line is your load line. With this point, we can fix the operating point where we can solve the IDQ in the graph. So this is called as fixed bias load line concept. So wherever you have the fixed point on the x-axis, if you keep here, the load line will be here. Operating point will fix there. If you keep here, it will fix here. Like that, you are fixing by the voltage your operating point. This is called as load line analysis, we can say. So we got a graph, we got a mathematics. This is called your first study called fixed bias analysis in the class. Okay. Conclusions I'll tell you at the end, whether which circuit is better, which circuit is not better. Final conclusion I'll tell you. First mathematics you complete. Circuit diagram and analysis. First finish off. They are very easy circuits, no need of having much tension. Very easy to understand it. Hardly one step, I got the relations and the graph. So please complete it. We'll go for the second circuit called self-biasing. So now you understood why it is called fixed bias means the voltage what you apply, negative voltage, I fix it to the VGS. That is called fixed biasing in effect or MOSFET. So complete this as a first circuit for you. Fixed bias circuit. Every time remember in biasing circuits in MOSFETs, RG, that is called gate resistance, will be disappeared in the class because of this knowledge. RG examiners will do, but you make it a short circuit because IC current will not be accepted to go to MOSFETs because of high input impedance. Yeah, Shabri, if you want, you can take no problem. This Kn without half also you can take no problem. But here in the formula you have to write half first, then Kn, then you can write, and you define the Kn as nu n Cox. That is our indication only. Okay, nothing to get tension. Tomorrow workbook may that Kn value they define it. According to that you inject into the formula. If half is not given, you keep half in your formula, and that nu n Cox W by L place में वो Kn value तो हो जाएगा. Okay, that is our indications. Suppose if I represent Kn here, you have to tell what is the total value there. I have said that its total value is that value. That's only my representation here. Anybody can represent whatever you want. Samantha is asking, sir, then what is the importance of RG? This RG you are making short, then what is the importance? That RG is not due to DC analysis. RG importance will come in AC analysis. It will play a role for you as an input impedance of the MOSFET. So in the coming class, AC part, RG will be there in the model. Only for DC case, RG will be gone. Okay? RG will be neglected for DC analysis. For AC analysis, we have considered it. Clear? Yeah. So let us move to the next circuit. That is called, next concept. That is called second one. Second one called as self bias. You already know this meaning self bias means RE bias, but here we are doing biasing by RS. Here source resistance we consider self biasing. So what is the change in the design from previous topic to present is? Here in fixed bias we don't have RS, in self bias we have RS. And RT is common, both have RT. This is VDD, and we have here one RG to ground. This is RG. This is gate, this is source, this is drain. This current is ID, and this voltage is VGS. So can you understand the difference between a self bias, how to recognize, and the difference between a fixed bias? You see the diagram, you'll understand clearly. See your notes, your diagram, fixed biasing. What is the difference you are observing is very important. In fixed bias, we don't have RS, correct? We have taken direct short, is fixed biasing technique. But in self bias, RS is important because RS will play a role of negative feedback. In BJT class, RE is playing a negative feedback. In MOSFET class, RS will play the negative feedback. So this is called self bias, the name we can tell. And here we are not taking any battery. Because in fixed bias, we have taken a battery. In self bias, we are not taking because the bias will be done by RS itself. That means biasing will come from RS only directly. So that is the differences. Like this, you have to understand the models. Yeah, every time VGG is negative, correct? Right? VGG should be negative because reverse bias we have to do, whatever you like. VGS should be reverse bias because it's a depletion MOSFET. So this first story I'll apply for this. That the gate current IC, we can take it as 0. IG, capital letter you can take, DC analysis. IG will take it as 0. No current will go to the MOSFET. Then this model can be represented as, you can convert that model like this. MOSFET, we have RS, this is RT. A direct short is there here. This is your VDD and this is your ID. And we have here VGS from here to here. This is gate to source. This is your drain. The circuit looks like this. Simple thing is, you just disappear this one. RG RG you have to make it as short. Nothing more than you have to do in the problems. So the story is like this. Now whatever the current you are seeing here, the same current will go down because they are in series. Now can you get a relation between VGS and ID? We can prepare one relation here. VGS, you can write it as VGS is equal to, actually 0 is equal to VGS plus IDRS. So VGS is equal to minus ID into RS, you can write. So this is the relation we are getting for cell bias. This is the relation we are getting for cell biasing. So VGS will become minus ID times of RS, which is looking like a Ohm's law. This is looking like a Ohm's law equation. The previous one is looking like a point on x-axis. Point on x-axis. Fixed bias is a point on x-axis method. There's only one single point it is. And here it's looking like a Ohm's law relation. VGS is equal to minus ID RS will be just like a Ohm's law. Now the point is VGS should be reverse bias, so minus ID into RS is a negative voltage. So I have been biased by MOSFET properly in reverse bias with this technique. Okay, without any battery, I biased it. Only thing is I have taken the help of ID, I have taken the help of RS. So but in these problems, if the examiner has given ID, I can solve VGS directly from the formula. If examiner has given VGS, suppose, I can find ID with this help of equation. There's no problem for that. But sometimes, to make lengthy the question, for 2 marks they'll ask you, VGS also you solve it, ID also you solve it by yourself. Then how the method can be applied? If I want to solve both the answers by myself, then what is the procedure we have to apply? If examiner is given, no problem. I can solve the other thing by this relation. But both the things I want to solve. Then what is the trick case? You just write ID equation first like this. Minus VGS by RS. You take this as equation 1 from the circuit design. I'll solve both the things now. How the technical applies here. ID is minus VGS divided by RS. You take it as one equation. And not only that, we have our equation, transfer characteristic equation, which is Kn into VGS minus VT whole square. This is our equation called graphical equation. So like this you write your transfer characteristic equation. So what I'll do is, in this also ID VGS are related, circuit wise. In your graphical equation also ID VGS are related. Then what I'll do is, I'll keep my first result in second result. My first equation, I'll keep in the second one. Then we'll get here, minus VGS divided by RS is equal to Kn into VGS minus VT whole square. You'll get like this. Minus VGS divided by RS is equal to Kn into VGS minus VT whole square. If you see that this expression is looking like a quadratic equation, A minus B whole square, if you expand, it looks like a quadratic style. You'll get a formula A into VGS square plus B into VGS plus C equal to 0. This structure will convert the form like this, which is nothing more than a quadratic equation. With the help of this quadratic equation, the person will solve the roots for that. You'll get a VGS operating voltage as minus B plus or minus root over B square minus 4AC divided by 2A. By using this quadratic method, you can solve the VGS value. Definitely in the subject, you will get 2 values compulsory. Okay, then how to justify which value is correct? For example, my answer is coming here, minus 2, minus 8, suppose. This is my choice of answers I got. Then minus 2, minus 8, which is correct answer, how to justify? For that, the simple knowledge is, confirm the pinch off voltage, confirm the threshold value. Confirm the threshold value. Okay, for example, in this problem, your threshold value, if you say, for example, the threshold for this question is minus 3 volts, suppose. This is the threshold value. If the threshold is minus 3, then I think minus 8 is wrong answer. Because you cannot cross the threshold voltage. You will be within the limits of threshold, the value, current will decrease. Above that minus 3, the current will be 0. Then how you got minus 8? So it can be identified by threshold knowledge. Okay, one answer will come below the threshold, one answer will come above the threshold. If it comes above, you just cancel it. This is a one way of trick. And suppose my answer is minus 2 plus 2 you got. I think for this nothing is required. Threshold knowledge is also not required because the depletion MOSFET VGS cannot be positive, it will be negative. So it doesn't go because it's a depletion type. It's a depletion type. So for depletion type, VGS cannot be positive. Like that you can tell the answers for the samples. So this completes my VGS knowledge. One time VGS is completed, you can find out the IDQ. IDQ is nothing but now you substitute in your original Ohm's law equation, you'll get it as minus VGSQ divided by RS. So this is the way how to find out the operating current. If somebody has not given the values, this is the procedure you have to do it. That is the reason we are not believing only the mathematics today. We are just finding the graph also side by. If the mathematics becomes tough for you, we'll go for graphical approaches. So both methods we'll try to understand. In BJT class, mathematics is easy because we don't have any quadratic methods there. But here we have parabola equations. Because of that, quadratic equations will come to solve these problems. But maximum in the exams, ID or VGS, they'll try to give for you. If they give one value, solving the other answer is easy from this straightforward formula. But if they don't give, then this is the procedure for it. Okay? Then how to draw the graph for this? Load line graph for this question. That also will complete. See here. Load line graph I'm drawing. This is your graph. VGS. This is your ID. For example, what we'll do is, we'll fix this resistor as 1K, cell biasing resistor. In the lab, I fixed RS is 1K. Then how to get the load line is, suppose if VGS is minus 1, VGS is minus 2, if the VGS is minus 3, I've taken some samples in the graph. Okay, gate to source voltage is minus 1, minus 2, minus 3. You said this RS value is 1K fixed. Cell biasing resistor is fixed. This answer you said minus 1, it will become 1 by 1K. It's 1 milliampere you are getting. If you keep 2 by 1K, it will become 2 milliamps. If 3 by 3K, it will become 3 by 1K, it will become 3 milliamps. So I think your answers will come Ohm's law. It will be just like Ohm's law samples will come. You'll get like this from the Ohm's law equation. This is one sample. This is another sample. This is another sample. What do you mean by Ohm's law means? It's a linear line passing through origin. It is coming on the negative side. Because it's a negative Ohm's law we're getting. There's a negative Ohm's law. You're getting Ohm's law here. So this is the way you're getting a linear load line with this concept. And then one after doubt, most of the students will get the same doubt. Whenever the person said here, IG is 0, RG is not open, my friend. Examiner BU, RGS 1 megaohm. What is really open in the circuit is, not RG is open, your input is open. Your MOSFET is open. Your current is going to the MOSFET. MOSFET is open here. Means what? No current is going to the MOSFET. But there is some resistance in series. but the resistor into IG current will be 0, then voltage drop will be 0. That I am telling you. Okay, examiner will tell you resistor value, how you will open it. Okay, here open meaning is not resistor is open, here MOSFET device is open at the input because you are doing reverse bias. Okay, understand that, Rahman? It's a common doubt for most of the students. That's why I'm explaining you. Here open is not resistor, here open is a device. Device is open because input is reverse bias we have done. Okay. Yeah, VGS should be negative because input should be reverse bias. So this is my load line. This is my load line. You have an experimental graph, no? You have an experimental graph like this. This is your experimental graph. Okay? This is your experimental graph. Can you see that it is exactly intersecting at this point? Your graph is intersecting with your load line there. So this point will decide. This point will decide your VGS Q value, and this point will decide your IDQ value. This is called as Q point. And the slope of this line is 1 by RS with minus sign. So it is having the slope of minus 1 by RS. Okay? So this completes my mathematics and graphical approach. You can see how much easy this topic is. Cell bias means you have some typical mathematics. If fixed bias we don't have any typical mathematics because X point we found, Y point directly we got from the formula. But in this topic definitely we have to go for quadratic methods to solve this type of questions. But maximum 90% in exams, gate exams or ESE exams, they try to give one value, we have to find the other value from the basic equation. So equation भूल नहीं जाना यार. बोर्ड देखते हैं वो equation आ जाएगा, Ohm's law equation. So complete this. We have one more bias is left over. That is called voltage divider bias. That will be the final biasing. So who knows PGT classes? There are simple things to learn. I'll take some water. Please complete up here. Yes, Pandit. Yes, Pandit. All the formulas are same here. This formula is same for everything. It may be enhancement you take, depletion you take, whatever you take. Only thing is, inside VGS values will change. VGS value is negative for depletion type. VGS value becomes positive for enhancement type. Nothing more than that. Okay? Inside the values change हो जाएगा. Formula will be same. That is the enjoyment you can do it. After linear line, the second line, how you have taken. Alright, Shavnidas, this is your line coming from the circuit. Correct? You designed a line from the circuit. But what is this line? This is called as a transfer characteristics experimental graph. You are doing some experiment in the lab. You are getting some graph for that. The graph is called experimental graph, called transfer characteristics. Your load line is coming from your circuit. Both are intersecting at one point. That is called Q point. Okay? That is called Q point, my friend. Shabnidas. Second line, what is the question? Number of times you have seen this graph, load line graph, and what can I say? The transfer characteristic graph number of times. Morning say, why teach ka depletion graphs? Okay? Very good. So let us complete the last one. Yes, Partha Sadhi. These concepts generally, we are fixing the operating point not in triode region, we are not fixing in ohmic region, we are fixing in current saturation because current saturation is called as active region in MOSFETs. BJT class, active region. Here current saturation we have to bias the transistors. That's why these circuits we are biasing in current saturation and we are fixing it. Okay? So that is the reason. That is the reason we take this equation only in the class. Current saturation equation only we take for study purpose. Okay, Partha? It is should be in current saturation. The last design here, final design. Topic number 3, which is called voltage divider bias. Voltage divider bias. This is the last biasing for depletion MOSFETs. This biasing, I think every student has been experienced in BJT class, so it's not a tough topic to understand. This is RS. We have some RT. Everybody knows how to design a voltage divider biasing. In BJT class, we have learned. This is R1, this is R2. This is your VDD. So if you see, it's a very common circuit. It will repeat in every device analysis. This is called voltage divider biasing circuit, which we have seen in BJT class also. But how to make here VGS reverse bias is the trick. Here we applied only one battery, but person is telling we'll make reverse bias. Correctly, if you see, this point is gate voltage. This is gate voltage. This point is source voltage. This point is VGS voltage in the class. And this current is your ID. So actually we want to make a gate to source voltage negative here. How I made is simple concept. First of all, what is gate voltage? Seeing the board you can write. Gate voltage. Coming from the BJT knowledge, it's a Thevenin's voltage. So gate voltage, we can solve it as VDD into R2 by R1 plus R2. So you can follow your BJT steps. It's a Thevenin's voltage I found is gate voltage. In this gate voltage. So after getting gate voltage, what is the VS voltage? Source voltage is ID into RS. This is source voltage. Gate voltage is source voltage power. But person is asking VGS should be negative. VGS should be negative you want in depletion biasing. In depletion biasing. If you want in depletion biasing, VGS should be negative. We have to apply a small condition here. There is a small condition we have to apply. What is the condition is? Your ID into RS, which is called VS voltage, should be greater than gate voltage. You design the circuit. There's a simple solution. ID into RS means this drop. Whatever you are designing in the circuit, that drop, source voltage drop, you just to maintain more than this gate voltage by the design. What do you do? That is enough. If gate voltage comes more than source voltage, it will become positive. But who will design source voltage more than the gate voltage in the circuit by using the choice of R1, R2, RS? Then automatically, I think your VGS will become reverse bias. So this point should be very carefully how to design the circuit. ID into RS should be greater than VG. That is the main important thing here. So this condition should be success. If this condition is success, now you can see that your VGS is reverse bias. Your VGS is reverse bias. Correct? If VGS is reverse bias, then what about the relation between VGS to ID? Your VGS is nothing but VG minus ID into RS. This is the relation we are getting. from the concept of voltage divided by RC. VGS is nothing but VG minus ID into RS. What is the type of equation we are getting here is, we are getting a straight line, we are getting a straight line equation. It's a straight line equation we are getting. So previously we got X point equation, point equation. Next we have seen the Ohm's law, and this load line, this circuit is giving a load line of straight line technique. Okay? Straight line technique is coming. Y is equal to mx plus c technique. So straight line is coming. Then we have how to find these two parameters at a time is, first you take ID equation from this straight line, Vg minus Vgs by Rs. You take it as equation 1. Just like previous method, quadratic method will solve. Second equation we have is your graphical equation, Kn into Vgs minus Vt whole square. You take this as equation 2. Equation 1 and equation 2 you can take. From 1 and 2, what we can do is Vg minus Vgs divided by Rs will be equal to Kn into Vgs minus Vt whole square. You can do like this. And we get a quadratic equation, A into Vgs square plus B into Vgs plus C equal to 0. If you expand it, we get a form like this. Therefore, Vgs Q answer, we can solve it. It will be minus P plus or minus root out B square minus 4AC by 2A. Same story. We have to apply this procedure to find out the two values if nobody has given the values. Any one value is given, this equation will solve it immediately. If I told you, we have to solve the quadratic method. After getting Vgs Q, then IDQ formula will be, it is Vg minus Vgs Q divided by Rs will give the operating current. This is the way how to solve the operating current in the class. So it looks like a similar topic, previous topic only. Just only thing is straight line equation we are getting in this concept by voltage divided by biasing technique. So how to draw the graph for this is the final issue. If I want to draw a graph for this is your VGS, this is your ID, this is VGS. You have a transfer characteristic graph like this. This is transfer characteristic graph. This is your experimental graph. Then how to draw the load line for this? It's a straight line equation, correctly if you see. If for VGS is 0, ID becomes VG by RS. Therefore, you may get some line intersection here, VG by RS. This is called ID max we got. If you want to be VGS maximum, y-axis should be 0. Then automatically VGS will become VG voltage. Your VG is a positive voltage here. Correctly if you see, this is the straight line, load line we got like this. This is the load line we are getting from that equation. X maximum value, Y maximum value I found. But I think if this line is not touching this graph, you cannot get the operating point. My load line is on the y-axis, on the first quadrant. Your experimental graph is in the second quadrant. Then how it is possible to design the operating point means this condition who will follow ID into RS is greater than the gate voltage. This line you can extend to the second quadrant. That is the meaning. That line will go to the second quadrant with this condition. Automatically you will touch the graph. Here operating point will be decided. So you can get here VGSQ and we can get here IDQ value. You can get the IDQ value. Okay? And the slope of this graph line is same 1 by RS. Here also we are getting slope as minus 1 by RS. Is it clear now? So this is the way how voltage divided biasing can be done. Now the student has to understand which biasing is better. We've done 3 biasings in the class. Next I'll give the overall conclusion. Which biasing is better I'll explain you in the class now. Okay? So which is the better biasing circuit? Let us understand the concept. So I'll give a small conclusion and we'll end up this concept. Then we'll go to the last topics that is called MOSFET, what I can say, enhancement MOSFET biasing techniques. One time who understood this topic, enhancement topics are very comfortable and easy for you. They will not take much time to understand. Only thing is in enhancement we have to take VGS positive, in depletion we have to take VGS negative, we have to bias it. Only the 2 points you have to understand. Okay, the others, I hope you understood it. Just to think about 1 minute, you will get the answer by yourself. So let us see which circuit is better. Okay? I'll give a good conclusion for you. Which circuit is better? I'll give a small conclusion to start the last topic. Why VGS is negative? Satyam, what is the question here? VGS should be negative. Why na? Pura kaam kar rahe hum. VGS whenever it is negative, the system is under depletion mode of biasing. Because in depletion mode, VGS should be negative. Correct? VT is unknown. Don't say like that. VT is not unknown. They'll give in the exams. VT compulsory. They'll give in the exam. Okay? In depletion mode, VT, they'll use some negative value in the problem. In every question, VT is a default. Okay? Here I'm not showing, but examiner will give compulsory VT value. Without VT, how you will solve these questions? If VT is there or not? If VT is solved, then you will not solve. Examiner will give that. And don't say that VGS is negative. क्यों हो रहा है? ऐसे नहीं बात करना यार. It is our intention that the MOSFET has to work in negative mode. That's why we are making some condition. VGS को negative करके हम biasing करके पूरा दिखा रहे concept. Okay? Let us see the conclusion of the class. So try to see a small conclusion. Small conclusion. For depletion MOSFET. For depletion MOSFET biasing. Depletion MOSFET biasing. The only thing you have to remember is, in all the cases, VGS should be negative is important for NMOS when you are doing it depletion mode. This is our trick. In every topic, VGS should be negative we have done. So, first point, fixed bias is always unstable. It's always unstable. Fixed bias is always unstable because operating point Q changes by DC battery variations, temperatures, and device variations. For all these cases, your passing is not a good passing. In BJT also same problem we got. Supply variations wise also we got problem there. And temperature wise also we got device means beta variations there. Here device means K and that all parameters if they change slightly, then automatically we'll get the variations more in the class. So all these things makes you disturbance for operating point in the technique. That's why we'll use fixed bias in amplifier topics. I'll say that your system is unstable. Your amplifier is unstable. So it is an unstable design actually. Fixed bias is not good actually. Fixed bias for any topic. It may be BJT class or it may be this class. VG by RS is experimental line here. This VG by RS, whatever you have seen, is my conditions I applied here. When VGS is 0, ID becomes VG by RS. That is the maximum limit of your line. If you want to write some straight line, it's a very simple physics mathematics here. When you want some x maximum, y should be 0. If you want y maximum, x should be 0. In that manner, I have written these 2 points from the equation. This equation I have taken the help. A equation help later, my straight line design here. Straight line limits. Okay? Don't say the word experimental line it is. Okay? This is called circuit line here. This is a load line come from the circuit. This is an experimental graph. Both are intersecting at that point to view. Yes, temperature wise, you will not have much variations. Okay? Not like no, BJT have more sensitive, but MOSFET will have less sensitive. I cannot say that completely it is temperature independent. Slight variations will be there compulsory. The disturbances also we can omit in the concept of biasing techniques. But fixed bias is not controlling that variations also. Okay? It does not have much variations. It is having less variations. Maybe these things I'll teach you. If you are an electrical student, I'll teach you these classes in device part. Temperature, how it will influence. These matters I'll explain in the device part when I'm teaching BJT classes. Okay? There we'll get that information. So let us come to the observation number 2. Second point, self bias is always stable. It's always stable. It's always stable with respect to DC battery variations, temperature, DC battery variations, temperature. Self bias is always stable with respect to DC battery variations, temperature. Okay? Why this DC battery variations go control current temperature? Why this controlling is? We have used a concept called RS technique. RS is a negative feedback resistor, which we have already experienced in BJT classes. Whenever you keep RE resistor, it has been given a controlling for the VCC variations. It has been a control to the temperatures. This RS always control these points. But device variations, it is not what you can say. It is not controlling much. The last topic is telling. Point number 3. Voltage divider bias. Voltage divider bias is always stable. It's always stable with respect to DC battery variations. Here also DC battery variations. It is controlling. Temperature it is controlling. Not only that, it is controlling the device variations. It is controlling the device variations. Okay? So the only difference between self bias and your voltage divider bias is device variations also it will control very nicely. Voltage divider bias compared to the self bias. Self bias is also controlling, but compared to self bias, voltage divider bias will control the device variations. So what is the meaning of device variations here is, suppose if you have the device like this, graphical device. For example, this is your device variation. This is the first device you have taken in MOSFET. Due to some reasons, the device has been replaced by, device has been damaged, you replace it. Due to that, we got some mismatch suppose. We got some mismatch. Your threshold voltage is slightly changed. This is VT1. The threshold voltage has changed to VT2. This current is IDS1. This current is IDSS2. IDSS1. So like this your device can vary. If you replace one device to other device, the threshold voltage slightly can change and your actual values are changing. Now, whatever the load line we applied, suppose this is your load line. This is your VT. This is the load line you applied. Now how to tell that the device variations is very small means the operating point, first point is here, the Q point of the first device. The second point is here. These 2 points variations, you find out your del ID value. This del ID change is coming very, very small in this voltage divider passing. So that is the main reason. The change in the ID current is very small. That's why voltage divider passing is giving a good results compared to the self bias also. Self bias is also good. Voltage divider bias is also good. But in terms of device variations, this circuit is more better compared to self biasing circuit. Okay? That is the main reason. Most probably you can go for self biasing or voltage divider biasing in electronics. If there is no device variation concept, only you have DC battery and temperature concept, you can go for self biasing. Because self bias looks easier to design compared to voltage divider biasing circuit. Okay? This is the conclusion of the total situation. Divya Das and one more person here. Majumdar, you are saying that sir, why you are using current saturation equation? But common sense use karo. We are working our transistors in amplifier region. Amplifier region in BJT class we call active region, but in BJT MOSFET classes we call it as current saturation. That's why we don't want to use triodes in the classes. We don't want to use ohmic regions. We want to use current saturation equations. That only I'm using it. Okay? For amplifiers we need current saturations. Then why you are getting that doubt? Morning onwards I'm telling you, current saturation is also called as active region. And the notes also have given the impact for. Okay? Then current saturation we have to use. Always the equation to solve these problems, which is a parabola equation in electronics. That we are using it. Ohmic reason guy. That is the reason. Triode is not an active region. Ohmic region is not an active region in MOSFETs. Current saturation is the active region. So please complete it within half an hour. We'll finish the final job called enhancement MOSFET also. We'll close it And in the board, I'll write the question numbers, what we can deal the questions. Okay, just today you can work out. Tomorrow we'll try to solve the problems in the morning. Can I come? Okay? So please complete up to here. Just half an hour, we can finish the module today. Tomorrow is very interesting modules are there. I think the depth will increase tomorrow, which is called digital inverter techniques. In digital electronics, you've done CMOS inverters, all these things, correct? But the birth of CMOS designs. CMOS inverter questions case analog electronics में. What is the concept behind that? Is the modules we have. You'll understand the beautiful techniques for tomorrow, which is our real estate techniques, integrated designs. By tomorrow, I cover all these things. So that the workbook we have a lot of questions based on this, what you can say, active load circuits we call this as. The techniques, all these things tomorrow class, we'll try to finish so that tomorrow we close the matter of MOSFET. But day after tomorrow onwards, we'll enjoy the concept of amplifier designs. Okay? Most of the people will feel very tough amplifiers, but I'll show you how amplifiers should be studied in the classes. How to make the amplifiers in the easiest manner, I can say. Best possible way, I'll try to deliver the class for you. Every student will feel comfortable after understanding the content delivered by me. Okay? You'll enjoy a lot amplifier questions. In every exams, compulsory amplifier question will be there in competitive exams. Most of the people will do wrong things because of lack of fundamentals. Each and every point, you have to consciously listen and catch that point. The trick will come from that to do the problems. Okay? Anyway, 3 days we'll work out amplifier designs. Each and every technique you will understand. After completing the last job is op-amps. We are coming nearer to the subject. Okay? Maybe next Friday, if you work out like this daily, 8 hours minimum, 7 to 8 hours if you can teach. At a stretch, by 7th or 8th, we can complete the total analog electronics. Okay? Maybe I got a call also after your batch immediately. I think I have to go for offline batch. Okay? Maybe I'm starting in Jaipur Center. There's a plan for me to start the class. After your schedule, I have a schedule again immediately to Jaipur. So that is my first offline class. Till now, I'm teaching this year and previous year in online. So maybe that is the happiest news for me as a teacher because I can see the faces of the students. Okay? I have missed that type of experience from 2 years onwards. Maybe in live, at least I'm seeing your messages and I'm feeling that virtually you are with me. That is somewhat happier to me. Okay? So op-amp questions is very tough. If you sit in my class, op-amps, कोई भी लेवो, BJT लेवो, MOSFET, op-amps, it looks silly for you when you solve my question, when you solve the questions. Only thing is lack of knowledge, lack of content, lack of techniques. You feel very tough. Okay? एक बार सुनो मेरे class, each and every point, whatever I'm teaching, if you are very sincere to listen my class, okay, lot of confidence will come in the designs now. Each and everything, happily you do it. Okay, that is my promise. That is my promise. Not only that, I'm also doing parallel with you all the questions I do in the workbook. Each and every question I solve it for you, then you get more confidence. Okay? Successfully we complete the module, analog electronics, step by step. No worries. I'm there with you, no worries. Ajandar, you'll become the expert in op-amps in the next classes. I'm promising you that. Yes, Roy, yeah, CMOS design is not done in digital. There's a chance to learn in analog. Okay? You have a chance to learn in analog electronics. I'll try to explain you how to design a CMOS. Tomorrow class is that only. That's why tomorrow class is an interesting topic. Yes, Swati, definitely. Tough will be there if there is a teacher who is not explaining properly. If the teacher explains everything in a beautiful manner, everything is easy one. Okay? I'll make you comfortable. MOSFET itself comfortable for you now. Yeah. Arpita, it's not the meaning that you'll miss us. These all things are not there. You'll always be in contact with them. You'll be in contact with me always. Okay? You have, I kept a group because it's a long journey with us. You're my students. Whenever you want, you can message it. Whenever I have free time, I talk with you. I'll message you. Personally, I'll give suggestions. Okay? So don't say that I'm missing you. Okay? You never miss me. Anytime, I'll be there with you. Always in contact with your WhatsApp. Okay? No problems. No worries. After 2 years also, if you give a message, I'll respond in the same manner. So lifelong, you're my student. Okay? I will be more happy that whenever you meet me, if you just wish me, I'll feel more happy. Unnecessarily, if you don't see me and if you go side by like that, that's not good. Okay? Whenever you see your teacher after 10 years or 15 years also, you remember your teacher. That will be the happiest point for your teachers. Arpita, I think I didn't get any information about Kolkata. Maybe Jaipur, it is open. Bhopal, it is open. Other centers, I think I didn't get any information. Maybe slowly, that also will start offline. Slowly, one by one, they'll start the centers. Okay? Now the situation has become normal. Slowly, everything will be going in good manner. So anyway, I'm so happy to complete my final session today. Let us start the enhancement MOSFET. Finish the 3 topics. Keep the heading. Enhancement, MOSFET, biasing. Enhancement, MOSFET, biasing. This is the concept we are learning today. Enhancement, MOSFET, biasing. In that, first we are learning fixed bias. Again, the story is fixed bias only we are studying. But the rule here is, remember, your VGS, you have to keep in mind, it should be positive. Nothing is there. We have to bias VGS positive. One time if you confirm that you have designed positive. Thank you, Shaw. Thank you very much. Thank you. So let us start to finish this today. We'll end up our class. First, to fix the bias, we are doing. Only thing is, the bias should not be negative. We have to make it as positive. Then how I'll fix the voltage? You can see the trick. In enhancement mode, what is my trick? You can see. If you see, in enhancement MOSFET, this is called fixed biasing. The student will get it out, sir. A fixed bias case this is called voltage divided biasing. How you are telling this is fixed bias? It's looking like voltage divided bias, sir. No, yeah. If you want to become a voltage divided bias, not only R1, R2, there must be some cell bias also required. If the cell bias, if you remove, only you kept the divided bias, we cannot call it as voltage divided bias. It will convert to fixed bias design technique. Why, sir? Means the gate voltage will become VGS directly. If the gate voltage becomes VGS, means you have fixed your operating voltage as VG. That is called fixed biasing you have done. So this is the trick called fixed bias circuit in the first lecture. Okay, so let us complete this trick. There is no here RS. There is not a voltage divided bias technique. So can you tell me what is VG from the board is? It is VDD into R2 by R1 plus R2. This is VG. Gate voltage is this much. And what is VGSQ? Directly here is. It is not more than your gate voltage. These two are same. because source voltage is not there. So because of this reason, we call this as fixed bias. We call fixed bias is nothing but a point on x-axis. We just fixed a point there. Vg is my fixed point. So this is called fixed bias technique. With this, how to find IDQ? Your IDQ will be equal to your Kn into VGS2 minus Vd whole square. With the transfer characteristic equation, we can solve it. So this is my operating voltage and operating current. Then how to write the transfer characteristics? You know that for enhancement mode, VGS will be positive, ID. So you have a graph like this. This is the graph of enhancement graph. Now you have fixed some point called Vg. Suppose the point, you have a parabola like this, suppose. You fix some point here, Vg. This is called a point. A point on x-axis is called fixed bias. Any point on x-axis, the load line will be like a straight line parallel to y-axis. So here you fix the operating point, where here we have the IDQ, that is called operating current. So this is the way how you done the fixed biasing. So I have seen that story number 1 is completed. The only rule you said, the VGS should be positive, so gate voltage is positive here. I made positive. So whenever you see this type of circuit in amplifiers in the coming classes, you can call this as fixed biasing amplifiers, fixed bias circuit amplifier. So finding the points is very comfortable. VGS you write as Vg, IDQ you solve with the transfer characteristic equation called as current saturation. This completes my first topic. Only 2 more designs. Only 2 more designs. So please complete it. I'll finish the 2 more circuits. This biasing looks very easy. Just one time practice the circuit and how to find out operating currents and voltage. Concept will be easier for you. So Ananya, Kolkata कब start होते मेरे को भी मालूम है. They have to decide. Management will decide and they'll inform you in the message. No problem. Just wait for their message. Okay? हम order नहीं कर सकते ना. According to the government issues, all these things management will take the point for that. So wait for some days. Anyway, our class will be going up to 7th or 8th. Meanwhile, you'll get the information. Okay? Our class होने के बाद ना, you'll have the offline. Until unless analog is not completed, you will not have any offlines. That's why wait up to 7th or 8th. So let us have the next design. We have 2 more designs. One is second one, voltage divider bias. Voltage divider bias. This is very easy now. Concept is very simple. Just apply the biasing circuit in voltage divider bias technique, where RS is required. For voltage divider bias, RS is compulsory required. This is R1. This is R2. This is your VDD. This is VG. This is VGS. This is VGS. This is VS. And this current is ID. The same current will flow here, ID. So how to solve this problem means simple logic. Your gate voltage is nothing but VGS plus ID into RS. Then what is VGS we got in the class is VG minus ID into RS. Already we prepared this equation saying that it's a straight line. Always voltage divided bias is a straight line. First confirm your equation straight line. It's a straight line equation. Load line will come like a straight line, intersection line. Now here VGS should be positive is asking. So only the condition will change from previous topic to present is. The condition here is your VG should be greater than ID times of RS. You have to maintain. I've seen the trick now. In depletion MOSFET, the condition is ID into RS should be greater than VG, how to set. But in enhancement MOSFET, it should be reverse because gate to source should be positive. That means you design according to that. Okay? You take this drop less, you take this drop more, then automatically it will convert into enhancement MOSFET because VGS becomes positive. That is the opposite technique. So, okay, so we can solve the value directly. If you want the IDQ, operating current. If you want operating current, IDQ, it is VG minus VGS, Q, your top line divided by RS. This will solve the operating point, straight forward. So I'm not doing the quadratic, all these things, you know how to do the technique. Just only I'm giving orally the main equation. If the examiner is giving this value, you can find out the IDQ directly. Otherwise, we have to go for quadratic steps, how I thought, in the same manner. I don't want to repeat the steps. So this is the main equation. If I know this answer, I can solve this. If I know this answer, I can solve this directly in the exam point of view. So this is called operating current. So how the graph you can draw for this? Graph is, for this you want a graph. So this is VGS versus ID. You want a graph? This is the graph. This is threshold voltage. So I already said, if you want ID maximum, VGS should be 0. So you have 2 intersection points. One is VG by RS, such that we apply the condition VGS equal to 0 here. And here one maximum value will come, where ID should be 0, VG by RS we got. And VGS equal to 0, so VGS equal to 0, VG by RS. If this is 0, it will be VG will come. So this is your load line. It is operating point. So this gives VGSQ and this gives IDQ directly in the graph. So this is a way how to bias the system with this technique. Okay? The same thing we can do for side by. One more design I can do it. I do it side by side, 2 designs. This is the second topic. And side by we can have same design with slight modification. That is called drain to gate bias. Drain to gate bias. This is a very simple design compared to voltage divider biasing technique. So what is the advantage of last design you can see? This is RD, this is VDD. Can you see what is the popularity about this last design? Try to understand. This is also a very good biasing circuit which will be used most probably by integrated designers. Why that last topic have that much importance? Okay? Shabani, in this case, cell bias will not work out because the only reason is VGS will become minus ID into RS will come. If I use cell bias, gate to source voltage will become negative. That is not good for us. Fixed bias, previous topic, negative battery is not good. That's why I'm doing like this concept. So cell bias is not better. Go for voltage divider biasing directly. Okay? Cell bias will make you negative bias if you do like that. Can you see that this is called a short technique? I already told you in the class whenever you short like that, this transistor will work in current saturation, I said. So it's already in current saturation technique. So we can write here VDS will be equal to VGS in this concept. Whenever you bias the transistor like this, VGS and VDS will become same. Okay? Then what is ID here from the output loop equation? You can write as VDD minus VDS divided by RT. You can see from the output loop equation, ID is nothing but VDD minus VDS by RD. So this can be written as IDQ if you want, VDD minus VGSQ divided by RD. So this is the way how I designed the equation. So you can see this equation, that equation, both have the same similarities. Here gate voltage, here VDD, directly we are getting. Here VGSQ, here also VGSQ, because VGSQ is nothing but VDSQ. Whatever the VDS you have, that is VGS. And here RD we got, here we got RS, they look same biasing techniques. But what is the popularity of the last copy case? It's the simplicity of the biasing technique. We don't have RS resistance here. The size is reduced there. And we don't have here R1 R2 resistors like voltage divided biasing circuit. So whenever you want to have a size reduction biasing technique, this technique is better. So this technique normally I use for VLSI integrated circuits. But when I go for small signal biasing, size is not a matter for you, for small signal amplifiers. Because amplifier system, we are not holding it, somewhere we are keeping them. That's why voltage divided bias is better for small signal amplifiers. And this is better for integrated designs in electronics. So this is better for small signal amplifiers. This biasing is important. For small signal amplifiers, we use this. But when I go for integrated designs, this I'll go for this, integrated amplifiers. This is better for you. So one is for integrated, one is for small signal amplifiers. Size technique is different. So what is the load line here? If you see the load line, this is VGS, this is your ID. You can have a graph like this. This is your threshold voltage. So we have a load line like this. This is a load line we are getting. We got a load line. Okay, we got a load line. So tell me the maximum limits now. VGSQ 0, if I keep ID becomes here VDD by RT, one answer. This is the ID maximum value. And if you want X maximum, Y should be 0. So you'll get the answer as VDD. These are the limits we are getting from your equation. Okay, there's only difference between these two procedures. So this is my operating point. So this will give VGSQ, this will give IDQ. So this completed my today course on biasing electronics. Okay, so one biasing is good for small signal amplifiers, one biasing is good for integrated amplifiers. Thus, both are advantages. If you are concerned with the size reduction technique, this is better. But when you are not considering size is not a matter, but you want a good output swing, suppose amplifier swing you want more, then this is better compared to that. Okay, here actually your swing will get reduced. What is the swing? Swing knowledge कैसे explain करना means amplifier में बताता हूँ कैसे explain करना. Here actually, if you use this biasing, your amplifier swing will come more like this. That is the advantage of using small signal amplifiers. But when I use this circuit biasing technique, your signal swing will reduce. There is a drawback here about swing. Okay, so in integrated electronics, if you are not bothered about the swing, but size is very important. This is called output swing. We can say output swing will be less here. We'll get less swing. Here output swing will get more. So how you got the swing knowledge, I'll explain in my amplifier design techniques. Okay, वो topics मैं amplifiers में continue करूँगा. So just have an idea, or have an idea like this. Just have an idea like this. Just copy it 1 minute. Just have a call, just 1 minute. I'll come back. Generally, graphical methods, we are not solving here in the exams. They'll try to give the values like this in the graph. With that values, we are trying to solve the other values. Graphically, we can't solve in the exams. They'll try to give some values there. Okay? If ID is there, they'll use some milliamps of current there. And we just go, please try to solve it, they'll ask you. At the time, use the equation and solve the concepts. So with this, for integrated technology, voltage diode biasing is more useful. Arpita, I think your statement, I'm not agree with your statement, Arpita. In integrated technology, we are not using voltage diode biasing, my friend. We are using this one. Diode connected MOSFETs, we call this as. Already I have written the board. That is for integrated. Because in integrated, size is very important. Can you see that the size is very small here? That's why this is for integrated we are using. Akshant, if you don't understand this, swing KSLSO, वो छोड़ दीजिए. वो amplifiers I'll teach you in the class, don't worry about that. Okay? In amplifiers I'll teach you. Here I'm not taught anything. Just I'll give the questions for you, just note down. Just try to practice the questions tomorrow. We'll work out the questions. So testing and biasing questions, what are the questions you can do? Just I'll give the overview for you. So note down please. So it is easy, any one book is enough here. Suppose in easy book you try to solve, tomorrow I'll write both the numbers because both the questions are similar. In easy book I'm telling, which is chapter number 4. Any one book I'm giving highlights for you. So this is question 1 we can do, question 2, question 4. Question 4, without knowledge we can do these questions. Question 8 we can do, question 9, question 12, question 14, question 16, question 17, D2, D3. So how many questions you can do it? These are the questions tomorrow I want to work out with the help of the knowledge of biasing and with the help of testing. ये questions कर सकता हूँ मैं. Okay? You try to solve these questions. Let us see how many questions you can solve. Okay? Let us leave the class. Thank you very much. Thank you very much.